Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. In this lecture video, I'm going to continue with the distributed forces, line loading or surface loading, and the way of transforming that line loading or computing that line loading into a force, single force with specified line of action. And also part of this lecture video would be to discuss about hydrostatic pressure, and which will be discussed in detail in the course hydraulics or fluid mechanics and hydraulics. So this is just uh, a direct way of discussing hydrostatic pressure because the pressure distribution is over a line or a surface or an area or a point, which is important as an application of the preceding topics on distributed forces. Level 53. The sides of a V-shaped freshwater trough shown in section are hinged along their common intersection through O and are supported on each side by vertical struts hinged at each spaced every 2 meters. Calculate the compression C in each strut. Neglect the weights of the members. So here's the given figure, and since this is zero point 0.6, let's consider the free body diagram of the left half, and some details will be, especially the distances, will be on the right half. But let's consider the left half. So for the solution, this is the pressure diagram. The pressure at the hinge O level is specific weight of water 9.81 times depth, which is zero point 0.6. And remember, by principle, the pressure is perpendicular to the contact surface. So this pressure is equal to 9.81 times zero point 0.6. This is the location of F, and it's the line of action of F would be 1/3 of the length of this contact length. This contact length can be solved by using this triangle here. Sine 30 degrees equals opposite 0.6. That's 0.6 there over this hypotenuse. So since sine 30 is 1/2, 0.6 divided by 1/2 is 1.2. So that's why, by the way, this is the pressure intensity, 9.81 times 0.6, and this length of contact is 1.2, which is equal to this. Therefore, this distance is 1/3 of 1.2, and that is 0.4. So I explained it in this video. Sometimes I purposely or intentionally remove all the details so that you as the audience will also think. I don't want you to just follow the very spoon-fed solution, because it will not develop your thinking analysis. So if I purposely remove some of the details, my intention is to let you improve, because you cannot improve if you keep on, if I make the solution very detailed in a spoon-fed manner that you don't need to think, you just follow. So at times you need to think also, but those are just mathematical details that I remove, basic mathematical skills, so details. So I hope that you will agree with me that the only way you can improve is to at times remove some mathematical basic details. So 0.4, 1/3 of 1.2, and the compression here, we'll call that C. So this is the reaction at O, to show that there is reaction here, so that the solution should be summation of moment, not summation of forces, equals 0. So that's C, and this distance is, because tangent of 30 degrees is 0.8 over this distance, so this is 0.8 over tangent of 30. So F is 1/2 of 1.2 times 9.81 times 0.6 times perpendicular to the board, which is distance 2 meters. So that's the volume of this pressure diagram, which is equal to this force here. So solving for F is 7.063 kilonewtons. So as I said, this is 0.8 over tangent of 30 degrees. So we can now solve for the compression C if we sum up moments about O, considering this left half. So C times 0.8 over tangent 30 degrees equals F 7.063 times 0.4. Solving for C is equal to 2.039 kilonewtons. Level 54, the solid concrete cylinder of specific weight 150 pounds per cubic foot, 6 feet long and 4 feet in diameter, is supported in half-submerged position in fresh water by a cable which passes over a fixed pulley at A. Compute the tension T in the cable. The cylinder is waterproof by a plastic coating. So here is the given figure. Then the tension in this cable here is also T, because the assumption is this pulley is frictionless. So that's T. Then we have the weight and subjected to buoyant force. The volume where buoyant force acts is only half of the volume of the concrete cylinder. So for our equation, summation forces Y equals 0. Tension plus buoyant force equals W, where the tension is the item in question. Buoyant force is specific weight of water, fresh water, which is 62.4 times volume displaced. Volume displaced is pi over 2, area of semicircle, pi over 2 times 2 square times 6 feet. While the weight is specific weight of concrete cylinder, 150 pounds per cubic foot times the volume of the cylinder, which is pi r square, pi 2 square times 6. So weight is 150 times pi 2 square times 6. It is 3,600 pi pounds. The buoyant force is 62.4 pi 2 square over 2 times 6. And it is 748.8 pi pounds. So substitute into this equation, T plus 748.8 pi equals 3,600 pi. So from there, we can now solve for the tension, and it is equal to 8957 pounds. Level 55, a block of wood in the form of a waterproof 16-inch cube is floating in a tank of salt water with a 6-inch layer of oil floating on the water. Assume that the cube floats in the attitude shown, and calculate the height h of the block above the surface of the oil. The specific weights of oil, salt water, and wood are 56, 64, and 50 pounds per cubic foot, respectively. So for the solution, we have the weight of the 16-inch cube block. The area of the bottom is constant, so we will call it A. Then we have buoyant force of oil, buoyant force due to salt water, due to oil. So our equation is buoyant force due to oil plus buoyant force due to seawater equals weight. The buoyant force due to oil is equal to specific weight of oil, which is in this case 56 pounds per cubic foot, times volume submerged in oil, which is area times 6 inches. So we don't need to convert 6 inches to foot, because we will use the height of each part into inches also. Buoyant force due to seawater is area times this submerged depth in salt water, which is 16 minus 6 minus h. So this is 16 minus h minus 6. And the weight is equal to 50 pounds per cubic foot for the wood. Then volume of the wood is area times 16 inches. So buoyant force of oil, 56 times area times 6. For seawater, 64 pounds per cubic foot times area. Then the depth of submergence is, as I said, quantity 16 minus 6 minus 8. So this is it. Then for the weight, 50 area of the bottom, although it is 16 square supposedly, but I just called it area because we can cancel area common to all terms in this equation, times height or depth of wood, which is 16. So canceling out area, then we have 56 times 6 plus 64 times 10 minus h equals 50 times 16. So only h is the unknown here, so we cannot solve for h. H is 2.750 inches. Level 56. A freshwater channel 10 feet wide, normal to the plane of the paper, is blocked at its end by a rectangular barrier shown in section ABD. So we have ABD. Supporting struts BC are spaced every 2 feet. So these supporting struts are spaced every 2 feet. So if we are asked to compute for the compression C in each strut, then we consider 2 feet, not 10 feet along the board, because the struts are spaced every 2 feet. So the tributary width to be considered is 2 feet perpendicular to the screen or to the paper. So determine the compression C in each strut, neglect the weights of the members. Since the slanted height is 4 feet, and this is 60 degrees, so this vertical distance is 4 feet sine of 60. And the pressure distribution is triangular. The pressure is perpendicular to the plane. So the intensity of pressure at A is specific weight of water 62.4 fresh water times height, which is 4 sine 60 as shown. So this is 62.4 times 4 sine 60 degrees, and we will call the equivalent force as F. As shown, the distance of F from the hinge A is 1/3 of this height, since it's of this length. Since this is 4 feet, so that's 4/3 feet. Then this is the compression of this strut BC. Let's resolve that into components. This is C sine 60, and this is C cosine 60. I will not call it C cosine 60 because when we sum up moment about the hinge at A, it has no moment arm, so it will just be 0. So this is C sine 60 because the angle here is 60 degrees and it is opposite of 60. So that's C cosine 60 supposedly, but it's useless to indicate or label it because it is not involved when we sum up moments about A. So summation of moment about A equals 0. But before that, let's solve for F. So this is the reaction at A, so that our equation is summation of moment, not summation of forces. So F is 1/2 of 62.4 times 4 sine 60 times 4 times perpendicular to the board 2 feet. So that's the volume, and the volume of this pressure diagram is this force here. So F is equal to 864.64 pounds. So summation moments about A equals 0. C sine 60 times 2 equals F times 4/3. So this is F and the moment arm is 4/3. Solving for C, the compression in the strut or every strut space to fit into the screen or into the paper is 665.6 pounds. Level 57, a channel marker buoy consists of an 8 feet hollow steel. So this is the hollow steel cylinder 12 inches in diameter, weighing 180 pounds. So the weight of this channel marker buoy is 8 feet. 8 feet hollow steel cylinder 12 inches in diameter is 180 pounds. And anchored to the bottom with a cable as shown. So this is the cable. If H is 2 feet, if this is 2 feet, so that means this is 6 feet. At high tide, calculate the tension T, so tension here, in the cable. Also find the value of H when the cable goes slack as the tide drops. So the value of this H here when the tension here is 0, or it is the tension is slack or 0. Then the specific weight of seawater is 64 pounds per cubic foot. Assume the buoy is weighted at its base so that it remains vertical. So for the solution, we have the weight. This is 180 pounds. Buoyant force in the submerged portion in seawater. And we have the tension downward. So summation versus vertical equals 0. Buoyant force in seawater equals weight plus tension. Buoyant force in seawater is 64 specific weight times volume submerged. Volume submerged is pi 6 over 12, 6 inches over 12, so we convert that to foot to be consistent with the unit. Square times 6 feet, where 6 feet is 8 minus h, and h is 2 feet in the condition. Then weight 180 pounds, then we can solve for t. So 64 times pi 6 over 12 quantity squared times 6 feet equals 180 plus tension. From there we can solve for the tension, 1 to 1.6 pounds. And when at high tide, when the cable goes slack, then the tension is 0. So we use the same equation except the tension is 0 here. And the depth of submergence is now 8 minus h. So this is the unknown. Then equate to 180. So 64 pi quantity 6 over 12 square times 8 minus h equals 180. Solving for h, the only unknown here, h is 4.419 feet. Level 58, a homogeneous solid sphere of radius r is resting on the bottom of a tank containing a liquid of density rho sub L, which is greater than the density rho sub S of the sphere. As a tank is filled, a depth h is reached at which the sphere begins to float. So determine the expression for the density rho sub S of the sphere. So the analysis is we solve for, or we find an expression for the density of the sphere when the sphere is about to float, or when there is no reaction here. So in other words, weight is just equal to buoyant force, where weight is specific weight of the sphere, rho sub S, times volume of sphere 4/3 pi r cubed, and buoyant force is weight is specific weight of sphere, which is rho sub S times g, then volume of sphere 4/3 pi r cubed. Buoyant force is specific weight of liquid, rho sub L, times g, acceleration due to gravity, or density of liquid times g to make it specific weight, times volume displaced. This volume is volume of a spherical segment of one base, which is pi height square over T, quantity 3 times radius minus h. So weight equals buoyant force. Again, the weight is weight of sphere times g times volume of sphere 4/3 pi r cube. Then buoyant force is equal to rho of liquid times g, pi h square over T, quantity 3 r minus h. So we can cancel g pi over 3. G and pi over 3. So rho s 4r cube equals rho l times h square quantity 3r minus h. Distribute and break 4r square into 4r cube into 4r square times r. So rho sub s equals rho of liquid times h square over 4r square times r in the denominator. Then we have 3r minus h. So rho sub s therefore equals rho sub liquid quantity h over 2r square times quantity 3 minus h over r as shown. So rho sub liquid h over 2r quantity square quantity 3 minus h over r. So that's the expression for the density of the sphere. Although this is supposedly enough when this is 4r cube. Level 59, the hinge gate ABC closes an opening of width B perpendicular to the paper in a water channel. The water has free access to the underside here as well as the right side of the gate. So here, when the water level rises above a certain value h, the gate will open. So determine the critical value of h. Neglect the mass of the gate. So this is horizontal, so the pressure distribution here would be uniform, rectangular. And here it's from 0 to maximum at B, where the maximum pressure is gamma times H, the same as here, specific weight of water times H. So for the solution, that's the pressure diagram here, triangular, and this is specific weight of water times H. Let's call the force as F or F1, and this distance is 1/3 of H as shown. On the second part, this is the pressure diagram, rectangular upward, and the force is F2. The distance of F2 from the hinge B is A over 2 because the length AB is A, so that's A over 2. And the pressure here is specific weight of water H, that's the reaction at B. And this is also specific weight of water H because they are at the same level. These points are on the same level. So since weights of gates are negligible, so that means there's no reaction here when the gate is about to open. So the opening in such a way is that this gate is about to rotate counterclockwise, so that there will be no reaction here. So that means summation of moment about B equals 0. So F1 times H over 3, which is equal to volume of this pressure diagram, is 1/2 gamma H times height H, then times perpendicular to the board B. So that's the volume of this pressure diagram, and that volume is equal to F1. Simplifying, it is specific weight of water BH square over 2, while F2 is A gamma HH times B perpendicular to the board. So A times specific weight of water H, so that's the area of the rectangle, times dimension perpendicular to board to make it volume times B, so gamma of water ABH. Then lastly, summation moment about B equals 0, so F2 times A over 2 equals F1 times H over 3. Substituting, gamma water ABH times A over 2 equals gamma water BH square over 2 times quantity H over 3. So we can cancel gamma of water BH over 2. Gamma of water BH over 2. So what remains in the left side is A square, and in the right side H square over 3. So A square equals H square over 3. From there, H is A square root of 3. So that's it for this problem. Level 60, the rectangular gate shown in section is 10 feet long, perpendicular to the paper, and is hinged about its upper edge B. The gate divides a channel leading to a freshwater lake on the left side and a saltwater tidal basin on the right side. Calculate the torque M on the shaft of the gate at B required to prevent the gate from opening when the saltwater level drops to 3 feet. So this is freshwater, this is the saltwater. So when the saltwater level drops, then the gate is about to open in that direction, counterclockwise. That's why we need to compute this moment here to prevent the gate from opening. So when that happens, there's no reaction at A. So we'll just sum up moment about B. So pressure diagram on the left side, which is freshwater, it will be as shown. And let's call that the force as F1. The intensity of pressure here is specific weight of water, freshwater, 62.4 times depth. And the depth is 12 minus 3, 9 feet. So that's 1/3, because this is 9 feet, 12 minus 3. 1/3 of 9 feet is 3 feet. And the intensity of pressure here is gamma of water times 9. Likewise, on the other side, the pressure distribution is also triangular. And we have F64, specific weight of seawater, times depth, because H is 3 given here. So this height is 12 minus 3 minus 3, so 6 feet. So that's why this is 6. Specific weight of salt water, 64 pounds per cubic foot times 6 feet. So this is in pounds per square foot. And the equivalent force is F2, since the height or the depth of seawater here is 6 feet, so 1/3 of 6 feet, this is 2 feet moment arm. Then F1 is volume of this pressure diagram, 1/2 of 9 times 62.4. The base, the height is 9 feet, and perpendicular to the board is 10 feet. So that's volume, which is F1. So F1 equals 252.72 pounds. F2 on the other hand is 1/2 of 64 times 6 feet times 10 feet. So F2 is equal to 11,520 pounds. Then the last equation would be to sum up moments about B equals 0. So M plus F2 times 10 feet. The distance moment arm of F2 is from B is 10 feet, 12 minus 2 feet. Then equals F1, the moment arm is 9 feet, 12 minus 3. So M plus F2 times 10 equals F1 times 9. Substituting values of F1 and F2, so M plus 11,520 times 10 equals 25,272 times 9. From there, we can now solve for the moment in pound feet, 112.248 pound feet. So if expressed in keep put, because this is a very high value, to 4 significant figures, it is 1112.2 keep put. So that's it for this sample problem videos.